We finished last time talking about what did we do last time? We were talking about, oh God, I can't even remember. Let me pull up my notes. Oh, we were talking about torque. That's what we were doing. We talked about torque, and we finished last time talking about work and perfect rolling. Yeah, Tiana, I can answer your question after lecture. So today we're going to talk about something else, but before we change gears completely, I just want to mention one more thing about torque. So let's just say we have some object, right? Some random object with a whole bunch of forces on it at these places, say. Something like that, right? And let's say that those forces are such that the net force is 0. It just happens to be the case that the net force is 0 with all of these forces. So you might wonder, well, what can we learn about the torque in the event that the net force is 0? Well, what I want you guys to remember is that the net torque is just the sum of all of the torques from the individual forces. And those torques, given some pivot point, say here, those torques can be written as, say, R1 cross F1 plus R2 cross F2 plus dot, 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 where R1 is, say, the vector that points from the pivot point to F1. R2 is the vector that points from the pivot point to, say, F2, and so on, right? So those choices of R depend on the choice of pivot. So you might ask, what happens if we move this pivot around? What if we move it, say, to there? You have the same forces, the net force is still 0. How does the torque change if you're measuring the torque about some separate axis? So I'm not actually going to go over the answer. What I am going to do is tell you that this will be a homework problem, answering this kind of question. And then you can answer the same question. What if we knew that the net torque was 0 for every possible choice of pivot point? Like, let's say that the net torque was 0 if the pivot point was here, or here, or here, or here. What does that tell us about the net force? How can we relate these concepts by knowing things about either the net force or the net torque? And again, that will be a homework problem. So I just wanted to introduce that idea to you guys to get you thinking about it. So with that out of the way, we're going to start talking about static equilibrium, which is probably the most useful thing that future engineers learn in 9A, because it makes you, or it teaches you how to ensure that something won't fall over. And hopefully, engineers build things that don't fall over, I guess, unless they're supposed to fall over. So let's break down these words. So static means unmoving. Equilibrium means not about to move. So the end result of these two definitions really is static equilibrium implies two things. It implies that the net force is 0, and it implies that the net torque is 0. So if something is in static equilibrium, then both of these criteria must hold. This is what it means for a body to be in static equilibrium. However, things get a little bit hairy, right? Because, things get a little bit hairy because we know what it means to say that the net force is 0. If you add up all of the forces, you get a 0 vector, right? But what does it mean to say that the net torque is 0? And what I mean by that is, you can't just, like, if I give you a system, you can't just tell me what the torque is. You can't, in particular, you can't tell me that it's 0. In fact, I would need to give you a pivot point, and then you could tell me what the torque is about that pivot point. So how do we handle that? Like, how do we decide which torque is 0? And the answer may surprise you. Turns out that it doesn't matter. In fact, when we say the net torque is 0, all that's saying is just choose any convenient pivot point and calculate the torque and set it equal to 0. So you could ask the reasonable question, why is this allowed? Like, couldn't it be not 0 for some pivots and 0 for others? But if you guys think about this from a ground up perspective, think about what torque does. Torque makes an object start rotating about some axis if it's at rest, right? But if an object is at rest, static, and is in equilibrium, meaning it's not about to move, then regardless of the pivot of the axis or the pivot point that you choose, the object is not about to start rotating about that pivot point. If the object's just sitting there, the torque about every pivot point has to be 0, because if it weren't, then there would be some pivot point that it would start to rotate around. And so that's how we can tell that the torque about any pivot point is 0, because the angular acceleration about any pivot point is 0. So the net torque about any of those pivot points is 0. I know I just said the same thing 3 times, but I wanted to make sure that it's clear. That's why that works. Like, an object that's just sitting there can have no torque on it. Otherwise, it would be rotating. So let's, by the way, there's an example linked about this kind of thing. Oh, shoot. I forgot to link all of the problems that the example problems that I wanted to link at the end when I was writing this up. I will make an edit at the end of the lecture notes to include all of the links that I wanted to include, assuming we get to them. And I'll include those in the uploaded lecture notes. But anyway, so there's a link here that an example that you guys can check out. But some of them are missing, so if I don't mention them, still screen through and make sure that I didn't add any links afterwards. Anyway, so before we can proceed by just trying to do static equilibrium problems, we have a little bit of work to do. So first, we haven't even really discussed how to use like a picture to figure out the torque. So let's do that. Let's talk about using geometry to determine torque. So just as a quick reminder, the magnitude of the torque vector for a given force is the magnitude of the r cross f, where r is the vector from the pivot to the location where the force is applied. And this is just equal to the magnitude of r times the magnitude of f times the sine of the angle between them. And it turns out that, at least for a lot of what we're interested in, two-dimensional problems where things are just rotating in a plane, it's often enough to just know the magnitude and the direction, meaning the magnitude and then whether it's clockwise or counterclockwise. So, and you can determine clockwise or counterclockwise just by looking at the picture. So if you can figure out the magnitude just from a picture, then you're basically all set. You can write down what the torque is and whether it should be positive or negative. And so what I want to do is I want to show you a way that we can use geometry to determine this value. So in particular, we can use geometry in some instances anyway to determine either the magnitude of r times sine theta or the magnitude of f times sine theta. And once you know one of these, then all you do is multiply it by the other one. Like if you know f sine theta, then you just multiply it by the length of r, and then you have the torque. And that's relatively easy to do given geometry. So here would be an example. Let's say that you have a rod with, say, a pivot here, and a force is being applied, say, up and to the left at the top of the rod. So let's let that distance be d. And so we will write, so it's the force vector F. So we can break this force vector up into two parts. We can break it up into a parallel part, a part that's parallel to the vector r, and a part that's perpendicular to the vector r. This is F perpendicular, this is F parallel. And so F sine theta is the magnitude of the perpendicular part. That just is true. So what you can do is if you happen to know the extent of the force in the perpendicular direction from this vector, then you can just write that down without actually having to do a cross product or having to figure out an angle if you know that part of the vector. Alternatively, let me move this over a little bit. in the same situation, let's say that you don't know that the component of the force in the horizontal direction, and what I'm about to do is actually slightly more useful more frequently. Instead, what you might do, I just wanted to duplicate the picture, is you would extend the force line. And so you can extend the force line in both directions. And the reason why we do this is because we want to find the place on this line that is perpendicular, that forms a perpendicular line to the pivot. See how right here forms a perpendicular line? So if we extend that line to get a perpendicular, this is also known as finding the smallest distance between this line and this point. Then this distance here, that distance is r sine of theta. And you could check the geometry there. By the way, this angle here would be theta. You can check the geometry there, but that works out. So often it's just easier to just, wherever the force line is, just extend it. And then find the closest distance between the pivot point and that line. And that will give you r sine theta. And then you just multiply that by the magnitude of the force. So just to be clear, and this one on the right really is more useful more frequently. In this case, sorry, we would have that the torque, the magnitude of the torque, is equal to the magnitude of F times d perpendicular, the perpendicular distance, which is just F times d times sine theta, which is exactly what we expect it to be. This d perpendicular, by the way, often has a name. It's called the moment arm. So it is the perpendicular distance between a force and the pivot. It's this distance here. So this is a relatively useful way of finding the torque, because often you'll have some complicated scenario where you have, where like, what would be a good example? I'm trying to come up with, let's say you have a pivot point here, and a force is applied, and let's say you know the dimensions here and the dimension here, and let's say you apply a force, I don't know, this way. Well, if you know the magnitude of this force, you know that this is the pivot point. Well, you could find the torque that force induces by just extending this pivot point, and you already know that distance. That's the distance that you already know there. So it's a lot easier and a lot quicker that way, just by using the geometry to set up. So this is why one might want to do that. Okay, so that's just a quick refresher, or maybe not refresher, a quick, easy way to find the torque. And then you'd have to determine whether it's clockwise or counterclockwise just by visualizing what kind of motion that torque would produce. But we will get to that. We'll get to examples. We still have two more things to talk about, though. And that's that in order to compute torque, you have to know where a force is applied, right? But there's two forces that we haven't really talked about in detail that require that. Like, if I'm just applying a pushing force, I know where the pushing force is applied, right? It's just applied wherever I push. Like a spring is a pushing force or a pulling force. A tension is a pulling force, and so on. Except you were reacting with no. Oh. Okay. Yeah. I don't know why that happened. So we need to answer the question. Well, there's two more forces. Let's answer the first one. Where does gravity act from? Like, on what part of the body does gravity act from so that we can compute the torque, right? Because we've already established in lecture 19 that the gravitational potential energy only cared about the height of the center of mass. And we concluded from that we can kind of treat the gravitational force as if it only acted at the center of mass. But the question is that even true for, or is that true for torque? Because we did the calculation as it applies to potential energy. Maybe you need to do some other fancy thing to figure out. Thank you. Where do we need? Maybe we need to do some other fancy thing to figure out where the gravitational force is applied so that we can compute the torque due to gravity, because gravity can produce a torque, right? So let's work an example. So let's say that you have a rod. the rod is made of a whole bunch of different stuff. It's not uniformly dense. Let's say we put a pivot point on the end. And just for the sake of argument, let's make this x equals 0. This is supposed to be a straight rod, by the way. I don't know why you can't draw a straight rod. Good enough. Maybe this end is x equals L. Doesn't matter. So we know that gravity acts on everything, right? Like the pole of Earth, the pole of Earth's gravity on like every atom in my finger is the same. It's mg, where m is the mass of the atom and g is the gravitational acceleration. So what we can do is we can break up the rod into a bunch of tiny little bits. These are supposed to be infinitesimal, but they're obviously not. And then we can just look at the force that the pull of gravity has on each of them. And some pieces might be heavier, so they'll have more gravitational force because the force is related to mg. Some pieces might be lighter, and so on, right? But the force will be different at different places or on different chunks because the gravitational force is different. So the question is what is the torque due to gravity on this rod? And by the way, we don't know where the center of mass is. So let's just look at the torque due to just one chunk, or the torque due to one chunk of the rod. So let's say that chunk is at, say, position x and that chunk has mass dm, infinitesimal chunks, right? So for a chunk at that position, due to one chunk, with that mass, the torque due to that one chunk at that pivot point would be the mass, which is dm, it's mg, so dm times g, times the distance that chunk is from the pivot point, because it's perpendicular to the pivot. So in this case, it would just be times x, because x is the distance that it is from the pivot, and the force is perpendicular to the vector r. And so the net torque would just be found by adding up all of these torques. So we can write that. You're adding up an infinite number of infinitesimally small things. So this would be an integral of dm times g times x. We can factor out the g times dmx. And now we can multiply and divide by the total mass. So this is capital Mg times dmx divided by, and we're going to rewrite the total mass in a different way. The total mass can also be written as a sum over all of the infinitesimal masses. Right, so these two terms cancel out. One is the denominator and the numerator, both total masses. But this here, that's the expression for the center of mass in the x-axis. So this is mg times the center of mass in the x direction, which is to say that the torque here is exactly the same as if the force was just applied at the center of mass, as if all of the force was applied at the center of mass. The torque is identical, and that's just generally true. So what we can do then is we can just treat, and this is consistent with our conclusion from lecture 19 too. We can just treat gravity as if it acts from the center of mass. Why it just become xcm? Well, this is the definition. Like that's how you compute the center of mass in the x direction. Oops, I don't know what just happened. So now, whenever we have a problem where we need to find the torque on an object, all we have to do is know where the center of mass is, and then we can find the torque due to the gravitational force by applying the total gravitational force at that one point. Okay, so there's one more force that we need to figure out, where is that force applied? So second question, where does the normal force act from? Or the contact force? And so this one's a little bit trickier. So unlike the gravitational force, where we actually know what it comes from, it's the result of the Earth's pull acting on every atom in your body. The contact force is a little bit different because the contact force is just a compensating force. It just is what it needs to be so that the thing doesn't move, right? Pen is sitting on my hand. The normal force, the normal force on my hand or on the pen is everywhere the pen is touching my hand. And it's pushing up in whatever way so that it's not moving. In particular, it's not rolling, it's not rotating, it's just stationary. So the normal force really is only there in a static equilibrium setting. So we can use that to at least figure out what the normal force is doing while it is acting on a static object. So on a static object, and just static object meaning an object in static equilibrium, we can figure out where the normal force acts. And that's what we're going to do. So let me draw a picture. So let's say that we have a thing sitting on a table. It's just a lump of stuff. It's just a lumpy thing. The center of mass is wherever it is. Let's say the center of mass is here, maybe. I'm actually not going to draw that. I'm just going to draw the. So the question is, well, we know where the gravitational force points, right? It points down from the center of mass. That's what we just determined. So where does the normal force point? Well, what we're going to try to do is we're going to try to establish at what point can we treat the normal force as if it's all applied there, so that it acts in the exact same way that the normal force really acts. Because really, the normal force acts everywhere. Because the normal force is, electrons in one thing repelling the electrons in the other thing. But just like how the gravitational force was, everything is, or the Earth pulling on every atom in you, we can treat all of those repulsions as a single force at one location. That's what we want to do so that we can compute the torque easily. So we have to use the fact that the object is in static equilibrium. So we know that the normal force, if the only force that's present is the gravitational force, the object will just move downward. So the normal force is going to act to make sure that the net force is 0, because otherwise, so that the object remains stationary. So we know that the normal force has to have the same magnitude as the gravitational force, but where does it go? Well, let's imagine that we put the normal force here, right? Has the same magnitude as the gravitational force, but it's just somewhere else. It's applied at that point on the object. Well, now let's consider using the center of mass as a pivot point. Well, the gravitational force won't produce any torque because it is located at the pivot point, whereas the normal force will cause rotation this way. So the normal force can't be there because the normal force doesn't cause torque. It actually prevents torque, really. So where would the normal force have to be? Turns out it would have to be directly below the gravitational force, because then for any pivot point that you choose, the normal force can't produce a torque. For example, if we choose the center of mass, well, you have your r vector that points down, your normal vector that points up, your normal force vector that points up. The sine of the angle between those, sine of theta, is the sine of 180 degrees, which is 0. So that would produce 0 torque. And for any other choice of pivot point, say over here, you'll have that the torque produced by the gravitational force is precisely canceled by the torque produced by the normal force. That will always work out, and I challenge you to check that yourself. So this is just to say, if gravity is the only force present, the only other force, the normal force is in a vertical line, or is in, I suppose it's in line with the gravitational force, or yeah, with the center of mass. Otherwise, we get that the torque is not 0. And we can't have that because the object is by definition in static equilibrium. So what if instead we had the same object sitting on the same table, have the same center of mass, same gravitational force downwards, but what if now I push on it, say here? I'm just like pushing on it with my thumb, pushing down. Where's the normal force then? Well, now we have to think a little bit more carefully. So let's say that we put the normal force directly under the center of mass again, right? Well, then we know that whatever torque the gravitational force produced, the normal force would cancel out. but there's still the torque produced by that force left over. So it can't be directly under the center of mass. And in fact, let's just start checking other places. Let's say that the normal force is over here, just to see what happens. Well, then clearly the whole thing is going to rotate that way, right? That's fairly obvious. Force F points down, the normal force points up. The gravitational force might not do anything if you're rotating about the center of mass, but the point is the whole thing would rotate. What if the normal force was over here? Then it's not quite clear. But if you were to draw, say, a line this way, it would rotate this way around that point, right? Because you have these two forces, which would push down, and then the normal force, which would push up. So you'd get rotation around some point between F and the normal force. Oh, please erase. So that can't be it. It can't be over there. Well, the only other place that I haven't checked, and obviously I did it for this reason, is it has to be, what if we put it between the center of mass and where the force is applied? Well then, maybe if we check this place, maybe it'll rotate. Maybe it'll rotate this way. But the gravitational force is going to hurt that rotation, so it's possible that it wouldn't rotate. What if we checked a different place? What if we checked, say, I don't know, over here as our pivot point? Well, then these are both going to try to contribute clockwise rotation, but the normal force might contribute counterclockwise rotation. So regardless of the pivot point that you choose, it's at least possible that the torque would be zero. It turns out that the normal force does have to be applied between where the two forces are applied in this case, and we can figure out where. So let's call this distance here, let's call that distance d1, and let's call this distance d2. So we know that the object is in static equilibrium, so we know that the net force and the net torque are zero. So the net force is, well, let me just write this out. So we have static equilibrium implies the following. So we have F net is zero, which means that, choosing up is positive and down is negative, which means that we have negative mg minus F plus n should be equal to zero, which just tells us the magnitude of n. N is F plus mg. And then we have that the net torque is zero. The net torque is zero implies, well, let's use the center of mass as a pivot point, just because it's easy. So the center of mass, if the center of mass is the pivot point, then the gravitational force doesn't contribute any to the torque, because the distance between the pivot point and where the force is applied is zero. R is zero in this case. So, but I'll write it out anyway. We have the torque due to gravity plus the torque due to the normal force plus the torque due to the applied force F. So this is zero here. The torque due to the normal force, well, we can use this extended force line picture to tell us that the torque due to the normal force has magnitude n times d1. And we know that it will produce a counterclockwise rotation. I'm going to denote clockwise as positive. So this equation becomes minus n times d1. And then the torque of the due to the applied force F, again extending this force line. The distance is d2. The moment arm distance is d2. The force has magnitude F. And it produces a clockwise rotation about our pivot point. So here, the torque produced by the force F would be F times d2. That's equal to zero. Now we know what n is. N is F plus mg. So we have minus F plus mg, capital MG, times d1, plus F times d2 equals zero. And so we can just solve for the ratio of d1 to d2. It doesn't tell us exactly where it is, but if d2 is bigger, then d1 should be bigger. It was how did I determine the clockwise rotation? If there were no other forces present and this point was fixed, the pivot point, the object would rotate this way. If I apply that force F. Just imagine there are no other forces and just apply that one force. Which way would it rotate? That's the easiest way. So this is just to say that we have F times d2 equals F plus mg times d1. And so we get that d1 divided by d2 equals F divided by F plus mg. So this tells us given the distance d2 that the applied force is from the center of mass, this tells us how to find where the normal force is applied in terms of just the magnitudes of the applied force and the gravitational force. So this is something that you guys can do. Like we can now figure out where the torque or where the normal force has to be applied so that the net torque remains 0. That's important because now we can just use that information about where the normal force is in order to figure out, or in order to solve various static equilibrium problems like that involve normal forces. Now, what this doesn't take into account is what if the system is not in static equilibrium? Like, for example, what if the object was on its side, right? What if the object was like tilted? Well, then it's not in static equilibrium. So we need to figure out, actually, let me preface this a little bit more. We need to figure out what happens, or how does the normal force interact with rotational motion? And can the normal force be in different places? How will it interact when the object is potentially moving? All of this involves this notion of tipping and stable and unstable equilibria. So let's talk about the conditions of tipping. It's a long heading. So again, let's look at the example where we have our object is just tilted, right? So we know that the normal force can only occur. Oh, and here's our gravitational force. And let's say in this scenario, I'm holding the object up, right? Maybe I'm applying like a force here. And we know that the normal force can only be applied at a place of contact. That's why it's also known as the contact force. So the only place the normal force can be applied is the place where the object is touching the ground, here. So we know where the normal force is. And so let's suppose for a moment that the object is in static equilibrium. Right? This is a delicate balancing act, right? You have to have just precisely the right force holding it up so that it doesn't fall down. And by the way, you would also probably have to have a like a friction force pushing, say, this way. But assume that it's like bolted, that it's fixed to rotate around that point, for example. So if we change F, like if we make F smaller, in order for it to stay in the same spot, the normal force would have to be applied in a different place. Maybe it would have to move to like here, but it can't, right? The normal force can only be applied in one place. So if we change what F is away from the value that it had in the static equilibrium situation, then the object can't be in static equilibrium and cannot adapt and cannot move around like it could in this case, depending on how hard the force is being applied here. So the conclusion then is when an object's normal, when the location of an object's normal force can't move to compensate for changing forces on the object's situation is no longer well described by static equilibrium. And hence the object would fall over. Because, you know, the gravitational force can't change. It just is what it is. The normal force would have to change. It's the only thing that could change in order to compensate for the changing F. So that means that the object tips or falls over. So what's the takeaway then from this thought experiment? Well, in order for an object, for an object to not fall over, the base of the object, the thing that's touching the ground, must be below the center of mass. And that's only true if the gravitational force is the only force that's present, right? If we get rid of F, this thing will fall because the base is not below the center of mass. But if we got rid of F and, you know, maybe there was a, maybe it was like angled like that or something, so there's like a part of this that was touching the ground, then maybe it would stay up, right? It might balance because the normal force could shift to be directly below the center of mass, directly below where the force is applied. So we can actually define this notion of stability in this case, i.e. what does it mean for a situation to be in stable equilibrium, stable static equilibrium? What does that mean? We can actually define that in terms of how much something rotates. So we define the stability of a setup, and I'll give an example in a minute. The stability of an object, rather, or a system, by the angle through which it can rotate such that letting it go wait a minute, hold on. The angle through which it can rotate such that letting it go returns back to its original position. Is that good English? Let me check. The stability of an object by the angle through which it can rotate such that letting it go returns it back. By the maximum angle through which it can rotate such that letting it go returns it back to, okay, that's fine English. So it might sound kind of confusing. Let me just draw a picture. It'll be a little bit more clear. So let's say we have two triangles, or we have one triangle. So if this is the ground, you have a triangle. Here's the center of mass, say. The normal force is going to point straight up. And if we tilt the thing just a little bit, so that only this part's touching, still have your center of mass, but now the normal force is here, well, this would be an example of a stable equilibrium because you can rotate it, and we know from experience that the thing's just going to fall back into place. It will rotate back into its original condition. Can you have an object with 360 degree stability? No, no, it's supposed to be a period, sorry. So here, the torque caused by the normal force is counterclockwise, which restores it to its original position. You have an object 360 degrees of stability. I suppose a sphere. Yeah, a sphere would be, I guess, right? Because you could just like, actually, I guess it's, well, no, not really. I mean, if you applied a force to it to get it to tilt, then it would just roll until it was back at its original position, like angular position anyway. But no, usually things have have some stability that is less than 180 degrees. That's standard. Whereas, so this would be an example of a stable setup, and it has some amount of stability. Like you can rotate it maybe 45 degrees before it doesn't fall back to its original position. Whereas if you have this setup, you have the same triangle. God, I can't draw a triangle to save my life. You have this triangle. This would be an example of an unstable setup because initially it could be in equilibrium, right? The normal force is directly below the center of mass. However, you tilt it just a smidge. Now the torque is clockwise. It will cause rotation this way. And rather than tilting back to its original position, it'll just fall over. So this would have a stability of 0 degrees, i.e. if you tilt it even just the teensiest amount, it'll fall over. And so we define stable equilibria as those with non-zero stability measure, and we define unstable equilibria as equilibria where the stability is 0. And so I want to link back to this notion of stability that we talked about when we were talking about energy diagrams, because really this notion of stability that we just introduced is the exact same as when we were doing energy diagrams, and it's for the exact same reason. So let me go over this kind of quick. We just have to think about the energy diagrams in terms of angles. So what we're going to do is we're going to write the energy in terms of angle. So I'm going to have to draw a good picture here. So let's say that we have an equilateral triangle, right? Triangles are the bomb. Yeah, I can. You have an equilateral triangle, right? Sitting on the ground. So the center of mass, let's say that this height is y equals 0. The height of the center of mass is, turns out, oh, I need to fix that. It's square root 3 L over 6, assuming the equilateral triangle is uniform, where the side length is length L. And that's just standard geometry. You could work that out if you want. Let's say that we now tilt this thing very, very slightly to the left, counterclockwise. And so let's call this theta equals 0 when it's straight up, when the point is straight up. And let's call this theta, let's call it positive. So we'll have counterclockwise be positive. So then the question is where is the center of mass? Oh, sorry, the center of mass there is, and by the way, the reason why we care about where the center of mass is because that will tell us what the gravitational potential energy is. It should be a little bit higher up. Oop. Should be a little bit higher up. So this height, you could work it out in terms of this angle theta. It takes a little bit of geometry to do, but it's not so hard to do. This height is square root 3 over 6 cosine of theta plus L over 2 sine of theta. It's a little bit involved to get that, but it's not so bad. So if that's the height of the center of mass, we know that the height of the center of mass tells us how much the potential energy, the gravitational potential energy is. So what is the gravitational potential energy as a function of this angle? Well, in that case, the gravitational potential energy as a function of the angle is just m times g times square root 3 over 6 cosine theta plus L over 2 sine theta. And actually, this should be absolute value, sorry. Absolute value of sine theta. Because if you tilt it left or right, it's going to be symmetric. So now we can just draw an energy diagram, except now our variable, instead of being x or y, our variable is theta. It tells us how much energy it has depending on its rotational position, on its orientation. So the energy diagram looks like this. And I'm not going to draw, I'm going to assume that it, the shape does matter. No, this energy diagram that we're using here very much depends on this being a triangle. An equilateral triangle that's uniform. Like you'd have to work out the geometry for whatever object you have. It'd be different each time. I'm just giving an example. So in this case, the energy diagram looks something like this. And I'm not going to draw further than that because it starts to lose meaning. But importantly, so this is energy. This is theta. This is our variable theta here. Importantly, we have a stable equilibrium at theta equals 0 because the forces point towards that stable equilibrium, right? And we have unstable equilibria here and here. This occurs at theta equals minus pi over 3, which is unstable. And we would have equilibria, another unstable equilibrium occurring at theta equals pi over 3, which is unstable. So let's think about what that means. So when theta is when this angle is pi over 3, that's 60 degrees, that means the whole thing has rotated 60 degrees, right? 1/6 of a rotation. There are 3 sides, so that's not the equivalent of rotating, like doing a full rotation, so it's on the other side. It's exactly halfway. So this point here would correspond to when the triangle is directly point down, that angle there being 60 degrees. And so, of course, that is an unstable equilibrium, because if you move just a little bit in either side to theta, you either fall back to the stable equilibrium or you go to another stable equilibrium. So this is actually like, they just are the same notion. Stable equilibria are those where if you move just a little bit left or rotate just a little bit left or right, you go back to that original location. That would be anywhere here. And the unstable equilibria are the places where if you start somewhere and then you move either a little bit counterclockwise or clockwise, you fall away from that place. So it is the same notion. Now we have only 4 minutes left, which is not enough time to do what I wanted to do. But what I'm going to do is I'm going to briefly go over, oh boy, that's a long list. Maybe I can write these out quickly. I'm going to go over a list of 9 steps, and I'm going to summarize them. I'm not going to write a whole lot of words, but it is written out in detail on the lecture notes, as to how you can solve static equilibrium problems. Then I'll go over an example at the beginning of next lecture. So step 1, isolate the object in a force diagram. Whatever object you're studying, draw a force diagram for it. And this isn't always easy, by the way. Sometimes there are multiple objects in a system, and you need to pick the right subset of objects. Maybe it's one object, maybe it's more, that you draw a force diagram for, right? Step 2, you have to define a coordinate system. So for your force diagram, just like we've done in the past, you need to choose what direction is plus y, what direction is plus x. And then also, because there's torque involved, you have to choose which direction is positive torque, which direction is negative torque. That amounts to clockwise or counterclockwise. And usually you'll see me doing this. I'll do something like this, x, y, and then maybe I'll do that. I'll draw a little loop and put plus in it to indicate that that's the direction that's plus. And it doesn't have to be that. Maybe it's this. This could also be that. But the point is that's the way that I usually notate it. Or you could do counterclockwise is positive, whatever. It's a choice. Step 3, extend each force line with a dotted line. This is how we can find the moment arm, like we did earlier. And you want to do that like as far as it goes on the page, as far as you can, because you never know how much you'll need. Scroll, please. It's like I have to ask it nicely. Step 4 is just choose a pivot point. So you have to choose a pivot point and then stick with it for the rest of the problem. And it's not always the case, by the way, that the pivot point is the center of mass or some obvious place. Sometimes you can choose a very clever pivot point that makes your algebra easier. Step 5, find the moment arm. For every force. So you have a pivot point. You've extended the force lines. So now you can just use geometry to find the moment arm for each of those forces. Step 6, multiply the moment arm by the magnitudes, or multiply the moment arm, multiply each moment arm by each magnitude. No, let me rephrase that. Each moment arm by the, trying to write this out quickly, sorry, by the magnitude of the corresponding force. This will tell you what the magnitude of the torque is. It's the magnitude of the torque, it doesn't tell you the direction. Then you just determine the direction of the torque, of each torque. And you do that by just imagining what direction would it rotate in if there were no other forces present besides the one that you're looking at. Step 8, add up all the torques. Really, I should do this. I'll just summarize it. Net torque is equal to 0. Net force in the x direction is equal to 0. Net force in the y direction is equal to 0. Add them all up, set them equal to 0. Usually, your solution comes about by and then maybe I should put and solve. For whatever, solve for whatever thing you're trying to solve for, whatever the problem asks. If it's true that your solution doesn't involve the thing that you're trying to find, if it doesn't work, go back to step 4 and choose a different pivot. Choose another pivot and repeat. Repeat 5 through 8. And those are the steps. That's how you do physics. Not physics, that's how you do static equilibrium problems. It's these 9 steps-ish. Now, just to be clear, sometimes if you choose a good pivot point, you can actually get away with not doing a few of these. Like if you choose a very good pivot point, sometimes you don't even need to worry about those. Sometimes you can just use the torque, for example. But you'll learn how to actually choose good pivot points just with practice. So that takes us through to the end of, well, I would have wished to have gotten a little bit further. I would have liked to have done an example, but that's good enough. So let's end the lecture here, and I will take